Hi, I'm Bartosz Polaczyk. I also work at Grand Parade. Welcome to a presentation titled "Seal All You Need to Know About Swift Intermediate Language." I will talk today about some low-level stuff that happens in the Swift compilation. So I am aware that not many of you have contact with it on a daily basis. That's why I think it will be better to first you give introduction into compilers and Swift compiler, so we'll know where exactly Seal is located in a compilation workflow. Here is the agenda. So as I said, I will introduce you into compilers. We will take a look how does it work on Swift sample compiler. Then we'll go into main part, Seal, and at the end, of course, summary. So starting with compilers. I suppose that all of you understand that any compiler itself, it's not a simple project, and as any other sophisticated application, it has to be well organized with a clear separation of concern. That's why compilers consist of three main parts usually: front-end, middle-end, and back-end. That's quite easy to remember. However, for some compilers, both front-end and middle-end are just linked together and called front-end. So this is the case with Swift compiler, where for brevity we're just distinguishing front-end, which is responsible for front-end and middle-end, and back-end. What are responsible for these parts? Starting from front-end, some languages have preprocessor. Swift doesn't. And preprocessor is responsible for editing your source file in somehow. And then, in the first compilation process, first step goes tokenizing. Compiler takes your source file and split it into simple, small chunks of your code. So some sample of tokens could be opening curly braces, quote character, or keywords like if else. So in general, this is quite simple step. The next step is called parsing, and compiler takes the list of your tokens from previous step and tries to create an AST, abstract syntax tree. Abstract syntax tree, it's a one-to-one representation of your code that you wrote, for instance, in Swift, but in a tree structure, which is then easier to work on in the further process, in further steps. In this particular point, compiler is 100% sure that your code is syntactically correct. And once you know it, it can go into semantic analysis. Mostly in semantic analysis, it performs checks that all your types match each other. And after we had a semantically correct representation, we can go into second block, middle end, which is responsible for analysis and optimizations. Optimizations could be like dead code elimination or tail recursion, for instance. What I wanted to note here that after end of the middle end, compiler is completely unaware of what kind of architecture it is compiling to. So no matter if you're compiling for x86 or ARM64, these are all the same steps. And on the back end, it's responsible for creating machine-level optimization for a specific architecture, for a specific processor, and of course, at the end, generate code, instructions that can be run directly on the processor. This is the general overview, broad overview of any compiler. Now let's move to the Swift, and let's start from the end. Not from the start, but from the end, from the backend. Some of you may already know that Swift reuses the existing backend compiler called LLVM, and is exactly the same backend compiler as Objective-C uses. So, what is LVM? LVM, as I said, is a backend compiler. It outputs unlinked machine code object file .o, and at the end, it takes LLVM IR in the front. So LLVM intermediate representation. What is it? It is defined as an assembly code of some theoretical processor. There is no processor on the world that can understand that. It is created only to feed LLVM backend compiler, which creates machine code as an output. In general, any backend compiler is actually quite complicated because it operates on a low-level abstraction, and that's why many compilers try to reuse existing backend compilers, backend parts, rather than creating new one. And as I said, Swift reuses the same backend LLVM as original Objective-C compiler, which is a C-lang. C-lang can compile C, Objective-C, and C++ languages. But there are many more languages that use LLVM under the hood, to mention Rust, C#, or even Kotlin. If you are not aware, despite the most popular Kotlin compiler that uses JVM, there is also another compiler called Kotlin/native, which uses LLVM to create machine code. And those Kotlin applications do not rely on JVM anymore. Those applications can be run directly on the processor. Okay, so we know the backend. Now let's go to a Swift compiler and take a look every single step from the beginning. As I said, we have a Swift file, and we are going to the first step. Actually, the first step was tokenizing, but it was really simple, just to splitting into small tokens your code. And the first step is parse. As I said, to remind you, it creates abstract syntax tree, one-to-one representation of your Swift code. What's interesting, with Swift, we can very easily observe the output after each step of a compilation. So how to do that? How to get the output of it? The easiest way is to open Xcode, go to Report Navigator, find your compilation Swift file, and then extend the view using this button, and you will see terminal command that Xcode uses under the hood. By default, Xcode in debug build builds for every single Swift file that you have very similar command in the terminal, just because it uses single file mode by default in debug build. As you see, there are many different arguments that we will skip at the moment, but if we add an extra argument -parse, we will be able to see on the console output what is the AST after the first parsing step. So let's have a look. And just for reference, I presented you the Swift file that I used for compilation. You don't have to really, at the moment, try to read it. We'll come back to it. But I believe that if I show you AST, with some zoom, you will be easily able to understand which nodes in the tree correspond to which part in the Swift file. This is one-to-one representation, self-explanatory. What I wanted to note here, that we've got variable var. And since I, as a Swift developer, didn't provide actual type of it and let compiler infer it, it's still in an AST, and after the first step, it's still unknown. It doesn't know that it would be Swift. So that was the first part. First step, we used -parse. We can take a look for the next step output. It was semantic analysis. We, of course, can serialize output, and let me demonstrate for the same file how does typed AST look like. This is just a part of the output, but if we take a look into a variable now, it's already Swifter. So after this step, we are aware of what actually types the compiler should use. That was the second step, and let's go further. The last step of the Swift frontend is a seal generator. And as the name suggests, it creates the seal language. Let's take a look how it looks. Oh, it looks like that. So our representation gets a little bit fuzzy. It's some kind of, looks like a mix between some assembly code and maybe some Swift. We will move back into seal in a minute, But at the moment, just take a look how does it look. Yeah. So that was front end, and output that we've seen called raw seal is passed into the middle end. There is increasing lines of code because as we are going deeper and deeper in the compilation, our concise Swift instructions are just split into smaller instructions. Okay. In the middle end, we've got seal optimizations, so the main part of middle end. And output of it is relatively simple, relatively similar to the previous one. That's why I will not show you on the slides. But we'll take a look into LLVM-IR, so the output for the next step. And it is a LLVM-IR. So as we are going lower and lower in abstraction, this looks more esoteric. And last block, backend, we received LLVM-IR. Backend is responsible for creation some optimization for a specific architecture and outputs machine code. Obviously, we can also take a look into assembly code, into string file. And this is something that most of you already seen in the Xcode, just assembly code. So that was entire process of Swift compilation. Let's recap. We had a front end for parsing, ensuring all the syntax and semantic and correctness. In the middle end, we had some optimizations. And depending on which architecture we are using in the backend, LLVM creates machine code for specific ARM64 or x86 architecture. Now we'll move into Swift language. So it is located in the middle end, and originally it was developed to make optimizations easier, just for Swift team to create optimizations over here. So what we will now be taking a look is located, it's used in the middle end in the seal gen step. Swift intermediate language, as the name suggests, is a language. And it is a fully fledged language, so I could technically introduce you with entire syntax of it. But rather than this, I think I would just give you the most important properties and just let you know what kind of information you can find there. For that, we will use the samples that I've already presented you. So let me give you a moment for read and understand what's actually going here. It's not so complicated. I suppose all of you already know that. This is just truncating your long title if it's longer than 10 characters with some ellipses. And if it's shorter, then just returns the same string. Even it's so simple, it includes some one branch, so the if here, and also some syntactic sugar, where we're adding this ellipses on the end of a value variable. So let's maybe just review the seal. It looks like that, so it's quite verbose. First characteristic. So every single line in seal consists of only one simpler instructions. And these instructions are just indexed with a number starting from 0, so %0, %1, etc. into infinity. There's no variables anymore. So let me demonstrate here. Every single line, we've got some index. Seal is strongly typed, so you will see exactly the same, almost the same type that you use in a Swift. So you will take a look and see the string type and also some pointer to the string. Third one, branching. That's quite interesting. What do I mean by branching, by the way? So branching is a is a breaking of your flow of instructions that we are executing depending on some condition. So the simplest branching can be caused by if. So whether we have a true or false, we may perform with different set of instructions. How is it represented in CL? So in CL, this function is split into several continuous building blocks. It means that it is impossible to break, depending on some condition, inside of building block only at the end of it. I know it sounds a little bit weird, but let's take the example. We have here a building block 0 at the top, and we have to execute all the instructions all the way down until the end of a building block, where depending on here on index 17 value, we are branching into BB1 or BB2. ARC, CL includes retained releases. So if you are curious where actually your retained counts are increased and decreased, you can take a look. Reaching comment. It means that maybe you've already seen that there are a lot of comments in the CL representation. Of course, those comments are just skipped by a compiler, but it is helpful for us to understand what actually going there, and we can use it for some analysis. So what kind of comments we can expect? Demanded function names, building block predecessor, and many more, but I wanted to concentrate on building block predecessors. So we have here the building block number 1, and it's exposed that the only one predecessor is building block 0. And it means that we can reach that point only from the building block 0. So where it can be beneficial? Now let's assume that you wanted to create a tool that counts, rather than line code coverage that Xcode creates, the branch path coverage. So you can just take a CL, try to analyze how many of potential branch your path, your code may run, and then try to estimate how many of potential branches your unit test should cover. So, for instance, it could be useful for creating such a tool. We've got also the BB2, where the predecessors are BB1 and BB0. Last but not least characteristic I want to present you is that CL can be used for code distribution. What does it mean? It means that once we received CL file in a text file, we can save it to disk, send it over the network, and then start creating machine code directly from that point, so skipping the previous steps. And this is super powerful. Let's imagine that you are creating some server-side applications, and for many different Linux distributions, you have to rebuild all the same code. You don't have to do it from scratch, from Swift, but only for CL representation. That's the first benefit that we can find that CL is useful. And the second one, that technically we can add some meta-programming in CL. Although I'm a bit skeptical about adding something there in production code, but it's possible to add some extra variables, some checks, and etc. So let's summarize the characteristics that we've learned about CL. CL actually takes your Swift concise instructions and split them into smaller, simpler instructions. It is strongly typed, so still keeps the track on all the types. Building blocks are split into continuous, functions are split into continuous building blocks. Includes some ARC retained releases. Reaching comments are very helpful if you wanted to create some tool out of it. And at the end, it should work to compile from CL. I said should because at the moment there are bugs still in the compiler, even in the trunk branch, but hopefully in the future Swift team will address that. So to summarize all the potential benefits that we can get out of CL, originally CL was created just to make Swift compiler team life easier, just to let them run optimizations. However, unless you are actually wanted to contribute into the score part, this is out of our scope. But if we are creating recompilation for different architecture, thanks that it still can be used for code distribution, we can speed up our rebuilding time. And also, it's helpful for some testing tool. I mentioned about path coverage, and also it could be possible to create some mutation tests thanks to seal. So what's our mutation test, by the way? Just to remind you, mutation tests in general they are evaluating whether your unit tests are correct. So they are checking that the potential bugs in implementation will be in tests. So how does it work? Assuming that we've got implementation already, somehow it works, it's defined in some way, we've got a set of tests that are passing, some green tests. That's the starting point. And then the tool takes your implementation and tries to mutate somehow. For instance, replace the plus into minus, the simplest one mutation. This is called the creating a mutant. And once we change the behavior of our implementation code, we are expecting that at least one test will fail. In case all the tests are still green, it means that we had a backdoor. We have a hole in our test. We are not verifying something. And as talk is cheap, let me just demonstrate the sneak peek of a tool that I'm currently working on. And of course, it uses seal under the hood. Let's go to Xcode. And here is a very sample class on the left, so implementation on the left, once more again, and a test on the right. So let's follow this. We have a class welcome that exposes one function welcome that takes a guest name string, saves the last recently welcome guest into a variable, and informs the delegate that new guest entered. Okay. The test also verifies one thing. So we are instantiating, linking delegate into a delegate mock here, and we are in act. We are calling the welcome function with guest one argument. Then we are verifying that the value is stored there. Yeah, looks okay, test. We've got already 100% code coverage, but let's try to run mutation test for that. Let me run it. This is implemented as a Fastlane plugin written in Ruby. What it does first is it rebuilds entire project. Takes a while. And the next step, it tries to find potential mutation that it can introduce. And we see that we've got 4 mutations over there. 2 of them are relevant at the moment, so referring to welcome class that I showed you. First one says that I can replace the body of the welcome function into empty function. Okay, another one, I can do exactly the same with info about guest. And then it performs all the unit tests according to implementation that the tool has changed. So we see that the first mutant has been killed, correct? But the second one survived. And what happened? Yeah, so I know that the mutation test replaced this function into empty one. So did something like that. Oh yeah, I completely forgot to verify my delegate mock. What was actually the appended here name of the string. Okay, so I have to write one extra test for that. Well, let's do it. Let's call it, we are checking that the delegate is informed. Act will be exactly the same, so we are still welcoming. and assert, we are expecting that here in the array of all welcomed guests is equal to one array with one element. Delegate mock, welcome names equal to. I think it's everything, I didn't make a typo. And let's run test again. Once it's building, I will show you here the simulator. Take a look what's happening there after the mutation applied. CEO found 4 mutations to apply. And here on the simulator we are seeing that it very quickly introduces mutation and then run unit tests for that. So it doesn't start from the beginning, it doesn't start rebuilding from Swift, it starts directly from seal. And great, we are kill another mutant over here. So we covered with an extra test, and the quality of our test increases from 20% to 50%. Yeah, of course we've got also some uncovered tests for updelegate, but this is something that I expect. So I'm not testing updelegate, so I don't care about those mutants. So as you see, we had 100% code coverage, but our tests were still missing something. And I could be able, thanks to mutation test, find and track where is the hole in unit tests. Let's go back to slides to summarize. So we learned at the beginning about Swift that it consists of frontend for specific Swift language. There is a backend, it reuses the same LLVM backend as Objective-C. If you are curious what are the steps in the Swift compilation, it creates a lot of options to serialize into an output, human readable output somehow. We learned also about seal. So we know that it is a simplified Swift representation of the code that you write. It's completely architecture independent because it sits in the middle end. Originally, it was created for optimization done by a core team, Swift compiler core team. But also, it can be useful if you wanted to create some tool, some third-party tool. So if you have any idea to help our Swift developers' life, make lives easier, now you can consider seal. Thank you, that's everything that I have today. Do we have any questions? Yes. Wait a second, where is the mic?
Do you need a microphone?
Yes, we need. Okay.
Thanks, great talk. Thank you very much. In this seal file, there is an intermediate step in compilation, but is there any information about Swift runtime in this seal file, or it is added later?
What do you mean by Swift runtime?
Swift have some runtime things like those retain release counters that is used under the hood, but if you write code in Swift, it is not visible. So does seal contains those runtime things, or it is added later?
Yeah. So exactly seal. There are two options or two representations of a seal. First one is called raw seal, before optimization, but after application of those ARC like retained releases, things like equitable, hashable, those things are added in seal. But also after optimization, there is a called canonical seal, and it also has some extra things after some dead code elimination and so on. So this part also includes all those magical things that happen under the hood.
Okay, thanks.
Okay.
Hello, thanks. So I have a question that what about if you have multiple tests, like a lot of tests, are you planning to make some optimization to make this mutation for all of the tests in the same time?
In parallel?
Yeah.
No. I think it's impossible because it uses the main thread, and if you wanted to run several tests on one simulator, it will break because it uses some global variables. Or maybe you're asking if we are trying to use a different simulator for increasing.
No, I'm asking about that.
Mm-hmm.
If you have a lot of tests and you can find for the 10 tests, let's assume 20 of mutation, so you'll be running in
20.
the next step, mutation. Yeah.
Mm-hmm. So for every mutation, I will run one test.
Okay. Thank you.
That's a good point because mutation tests can be long time consuming.
Thanks for a great talk. The question is maybe obvious, but the seal is written in C, right?
No.
It's
I mean,
Swift?
seal reader, parser, and then all the compilation, it's written in seal, in C. Because it's or C++, actually. Okay. Yeah, but seal is actually representation. So you can think about
No,
C.
I'm only talking about the the implementation itself. The
optimization.
representation, like it doesn't matter for me right now. The thing is, okay, we can benefit from it, but you have to know the C++, right? If you want to dig into it. But you were writing as far as I saw, some plugin for Fastlane, right? And you were using obviously our favorite language, Ruby. And what do you use for it? Do you handle it on only the output itself and parsing it by yourself, or you are using some external tool written, I don't know, in Swift or Ruby or I don't know what?
Yeah. So question generally is, how do I read? How did I read?
Exactly. How do you understand using the other language? Probably Ruby, what's happening inside seal, what seal is outputting to you.
So seal, it's a file, that's seal, it's a text file that I presented you, and I had to actually perform almost the same steps I presented in slides, so I had to take tokenizing, semantic analysis, syntactic analysis, and so on. However, I didn't make a 100% parsing of it. I was just taking the most important key parts of a seal representation just to take what I actually needed. As far as I know, there is no single seal parser in any language other than C++ that you mentioned. That's why I had to do it on my own.
Okay, so it's just a simplified version for now.
Yeah, exactly. I think nobody can reuse it.
Maybe that's your niche. You can create something custom in Swift.
In Swift, okay, maybe.
Okay, thank you.
Thanks.
More questions?
We've got one extra back.
Okay.
So a seal file is a text file, which means that I can write manually.
Yes.
Is there any reason or use case where it makes sense to write?
Oh, I don't believe so. It would be very complicated to write it. Oh, exactly the same you can do actually write LVM-IR. You can also write assembly. This is kind of same story.
I've written assembly.
Oh, really? Okay. So maybe we'll find...
It was simpler.
You may find C a very nice language. Thanks.
More questions? I have some questions.
Yes.
So basically, the seal is our bytecode, the JVM bytecode, right?
Exactly. We can.
Yeah. So we have something like bytecode weaving, so we can change the bytecode of our program. So we are doing the same, right?
Yes. As far as I understand, what does you mean by that?
Yes. So because in Java we have to write a lot of boilerplate. Now we use Kotlin, but I'm talking about Java ages. And we have two ways to generate code. So we can use annotation processing, so we can pre-process something, so we can add more to our code, but still it's going to be Java and then compile
and then the compiler compiles it to the bytecode, and we have this bytecode weaving. And people, based on the bytecode, did a lot of stuff, and now it is said that it's horrible. Like they say that if you want to mess with the bytecode, probably there is something wrong with you. But
I agree. I said that
because it's dangerous stuff. Like it's pretty powerful. You can change a lot of things. For mutation testing, I think it's a more as an aspect of the programming of writing tests. So you actually use it to change it to get some benefit. But imagine the fact that some guy can do some wrong stuff with seal, right? Try to implement some analytics, for example, to pre-process, post-process analytics to seal. So, what do you think about?
That's too dangerous. Yeah, I'm totally against meta-programming,
Because
especially in seal.
Yeah, so because I know that you are a pretty fan of testing, that's why I think you research the fact of seal, and probably you want to build this library for mutation testing, and it's an awesome. But do you have any other ideas how to use it?
Any other than for testing one?
Use cases,
Yeah, I wouldn't recommend you to add it in production code to modify it. Yeah, generally, in case I did something wrong, what can be output of it? What can be wrong with it? Yeah, your mutation test will just say that you've got a higher or lower test quality. Nothing wrong happened. In case you've got some error in the production code, that's terrible experience. So.
Yeah. So
the tests are the maximum that you can.
Yeah, I know. This is the perfect use case actually, because I was wondering what is the use case for this. Just the last thing. You have a long block library that are using bytecode weaving to, for example, make your classes immutable or something like that. So this is something really strange to add features to a language because of the seal weaving or something, or bytecode weaving. Yeah. But thanks. Presentation great, I love it.
So I'm assuming that you'd like to release that library. What was the release date?
Unfortunately, I'm using Swift 4.2, or this is called still the master branch, because none of already existing released Swift version had a bug that I unfortunately or fortunately was able to fix on the Swift compiler repository. But every time I check on this new version from a trunk, it's still not ready for code distribution. That's why I said in theory or in the future, it will be possible to create out of a seal this code that can be run on the machine. At the moment, we still have to wait, at least for Swift 4.2. They are doing a lot of stuff regarding memory ownership. That's why all the time I found some versions, some trunk releases are more or less able to rebuild it from seal. That's why I cannot assure you that with Swift 4.2 it will work. Maybe 5.0 is rational to say maybe.
Okay, thanks. So with every version of Swift, you have a new version of seal? No?
Yeah, no. This is the language. The definition of seal is quite well documented, but guys are still adding some extra stuff that, for instance, they wanted to keep track of who owns the object, and that's why compilation crashes whenever you try to build from seal into a machine code. So seal will be the same, but you will not be able to actually create mutations.
Okay, so if you will create your library once, the seal will never change. Like you're just mutating the seal file, right?
I cannot answer that. I have no idea if they are planning to change seal in the future.
Yeah, because like for every version of Java, the bytecode is different. Because they are adding, changing stuff. Okay, thanks. And the last one. the LLVM. This is a really good stuff. That's why the Kotlin native can actually work on the iOS. So do you think that the Kotlin will be not maybe the main language, but one of the languages that can be used for iOS apps?
No idea.
You have no
I
idea.
have no idea. Do you have?
That's the problem. It's not like regarding the language. I mean, you can write the perfectly fine iOS application to ask it to work instead of VM. But the problem is like how do you show the button? That's the problem.
Showing the button.
No, it's not that simple.
Yeah,
Like,
yeah.
if it would be that simple, probably like I don't know, Facebook would so far like create something, but Facebook invested in something like React Native.
Okay.
And that's the problem because you won't have like first day cover, right? Like you need a new version of UIKit and you want to like, man, I have to like implement this stupid like slider because they fucked up completely everything.
Okay, so it will be not
So
possible.
everyone is scared, right?
Uh,
Apple has money. So
okay.
they
Yeah.
say what they do.
Yeah, that's fine. Thanks.
I think we've got one extra question.
One more from me. Is there any difference between seal generated on Linux with that generated on Mac?
No, this is still exactly the same. So unless you are using some client importer because you are importing different stuff from Objective-C, for instance, if you are creating a pure Swift code, it will be exactly the same. That's why you can take seal, create it from Mac, and then compile it for Linux.
Okay, thanks.
Okay. That's it. So give the big applause for Bartosz.